All right, so I am back out into the garden, and we're gonna do a little experiment with some beans. Just found some worms too. You see it? It's a little worm. Okay. We're gonna do some experiments with some beans. So I've got some jade beans here that I gotten just from the Fayette County seed exchangers, and then I've also got some top crop beans. And we're gonna take a look at these beans and what they're gonna do in the soil. Okay. So I'm just gonna get out 1, 2, 3, 4, 5 of each color of bean. Okay. Where the soil is really dark because it just rained. Okay. So I'm gonna get out 5 of each color of bean. One, 2, 3, 4, 5. Okay. So here I have my beans. I've got some white beans in there, and I've got some brown beans in there. And in this environment, if I zoom out a little bit, you guys can probably see that the white beans start to stick out and the black beans are really hidden, right? So here, if I am a predator, like an owl predator or something like that, and I'm swooping in, okay, so imagine the beans, instead of being beans, are like little, I don't know, little mice or something, right? If I'm an owl predator, I'm gonna come through and I'm gonna just pick out my beans, okay? 1, 2, 3, 4, 5. And it looks like the ones that I ate, that got eaten, where's my camera at here? That got eaten are 4 white beans and 1 brown bean, okay? So let's say that these little beans are going to replicate, okay? And the white beans are gonna stay white and make another white copy, and the brown beans are gonna make another brown one, okay? So here we've got a white that I'm adding, and 1, 2, 3, 4 brown ones, okay? So I had started out at 50-50. I had 5 white beans and I had 5 brown beans. But let's count now how many I have. So it looks like I've got 2 of the white ones, right? And I've got 1, 2, 3, 4, 5, 6, 7, 8 of the brown ones, right? So just in one generation, I've gone from a 50-50 to only 20% white and 80% brown, right? So natural selection acted really quick on this population to make it so that we have mostly brown ones. So I'm just gonna mix these guys up. If they get planted in my garden, it'll be fine. Okay, so I'm gonna come through as a predator again. I'm gonna pick out 1, 2, 3, 4, 5 beans. And you can see already, now I have no white beans left. Okay, so natural selection can act just that quickly, where we have our population going 100% to one type really, really quickly. Okay, and what I just did here was an example of directional selection. Okay, so let's draw out some of the different types of selection that can happen. Okay, so here I had variation, right? I had white beans and brown beans. Okay, so here I had my beans, where in the first generation I had 50% white and 50% brown, right? In the next generation, right, I had 20% white and 80% brown. So here I've had some evolution occur. And it was because we had that variation, right? Remember, the white beans always made white ones, and the brown ones always made brown ones. So we had heritability, and then we had differential fitness where it was better to be brown, okay? Now, this could be different in a different scenario. So maybe instead of this dark soil that I have, I was in a sand environment, a white sand environment, or in a white rock environment, then maybe it would have been better to be white, okay? So evolution occurred, there's differential fitness, and in this case it was due to an environmental background that was dark, right? So here I've had an evolution occurring. We've had a change in those frequencies over time. Okay? All right, I'm just wanting to change that just a little bit. Okay, so, and it was because of some mutation that had happened a long time ago that made it so that I already had existing white and brown individuals in my population. And the kind of selection that had happened in this case okay, is called directional selection. So originally we had a trait, our average trait, if we had white over here and brown over here. We had individuals that were white and brown, right? And we could have something, maybe also could have had something in the middle, right? And then this is like the number of individuals. And so if we're talking about a trait that maybe could have an intermediate amount, okay? So maybe we have a trait that is like light brown here. And maybe all of our individuals in the population had started out as light brown, okay? Maybe let's say that all my individuals started out as light brown, okay? Over time, I would have shifted, okay, to be all brown. So before selection, maybe I had some individuals that were white, some that were light brown, and some that were dark brown. And then after selection, it was better to be brown. Oops. So my curve has changed, okay? So this is called directional selection. And this is when the trait moves in one direction, okay? So in this case, it shifted from left to right. Now, if we're in a white sand environment, maybe I would have shifted toward the left instead, toward more white, okay? And when we have directional selection, we have a change in the average or mean trait value, okay? So here we had, the light brown was the most common, right? Light brown was most common, and now we're going to have brown being most common. And maybe over here we can shift it so that it is getting more and more dark brown or something, right? And then the other thing that changes is that I might tighten this curve a little bit, okay? So maybe we had a limit here. I want object eraser. Maybe I have a limit here where I can't get any more brown than I already am, okay? So maybe I've shifted it so that it's like this, right? Where I've got more and more individuals that are on that brown end, okay? So a lot of times this will decrease the variation in a population. So over time, right, I don't end up having any whites, right? And I just have a really tight brown curve. Maybe I have a few of the light browns left, but no whites, okay? And over time, maybe I keep on shifting that curve to get tighter and tighter and tighter. But directional selection isn't the only type of selection that can occur, okay? So maybe in this environment, instead of having this dark soil, maybe I had light brown soil, okay? And it was better to be light brown. So here instead, let's draw this out again. So I have my white, light brown, and dark brown, okay? And I have my number of individuals. Maybe my curve is the same before selection, where I have some white, some light brown, and some dark brown, right? I'm gonna copy this just so that I can have it for the next one that I need. Should I give myself a little bit more space? I'm gonna put it down below. Okay. So here, maybe it is best, move this over. Maybe it's best to be light brown, okay? Maybe, go back. Maybe the light brown is the best, okay? Maybe this is best. So if I'm in a light soil environment instead of this really dark soil, maybe I have a bigger mix of soils or something. Okay, maybe it's best to be light. What's going to end up happening is my number of individuals that are the light brown is going to increase, and my number of individuals that are the white or the dark brown are going to decrease, okay? So here, what's happened is I've had the average trait value is still the same. Most of them are light brown, right? So average value stays the same, okay? But there's it tightens quite a bit, right? There's a big difference in the variation. So there's a very striking decrease in the variation, where I maybe don't have any white or any dark brown individuals, okay? So in this case, this is called stabilizing selection. And stabilizing selection is actually pretty common. So this is the reason why babies are born the size that they are. So if babies are too little, then they are not going to be able to, especially historically, survive outside of the womb if babies are too little. But if they're too big, then they get stuck inside of mom and can't get out. So before C-sections, babies would get stuck in both mom and baby actually would die. So, so evolution has acted on us to have babies that are kind of just the right size, so that babies aren't too big or too small. Now, in our current environment, in our current state, we're kind of breaking some of those or bending some of those rules because we do have modern medicine to help us and do C-sections and have NICU stays so that babies are okay if they are not quite the right size, right? And then we could also have a third kind of selection that happens. And in this type of selection, there's no light soil, it's only white or dark, okay? So in this case, what color have I not used? Let's use yellow. It's best to be not the middle. It's better to be one of the two ends, okay? So it's better to be white, not good to be light, or good to be brown, okay? So in this case, right, we have no change in the average, because if you count all of this up, I'm gonna change that just a little bit and distribute it a little better. Say that we have the same total number of individuals. Oops, back. Okay, it's best to be white, not good to be light, good to be brown, okay? So in this case, we have the same average. So here, we have changed the average. So, we have kept the average just like we did with stabilizing selection, and directional selection is the only one where we changed it. So here we have the average trait value. Get out of the sun. My iPod's really, really hot. Okay. Average trait value stays the same, because if you add up all the individuals that were white, all the individuals that are brown, you're going to get an average trait value that is the same as what we had started with, okay? But the variation stays the same, or it could even increase. And this depends on what factors we have present. So a lot of the times when we're talking about these kinds of traits, actually, we're not just talking about one gene, but we might have a whole variety of genes that are playing a role in color and lots, shape, size, all kinds of things. Okay, so this last one is called disruptive selection. Okay. And these different types of selection are going to come back into play when we talk about speciation later this week as well. Okay, so those are 3 different types of selection. Disruptive, where we worked against the mean, the middle. We have stabilizing, where the middle is the best. And then we have directional, where one end is better than the other, of the spectrum is better than the other. Okay, so let's start looking at our learning objectives and see how we're doing with those. Okay, so let's first look at our just intro to evolution. Oh, it went to the top, didn't it? Okay. So here we have our intro to evolution, learning objectives, and let's make sure that we have all the different things. So first off, defining evolution. So let's make sure that we can define evolution. So this is, the change in allele frequencies in a population over time. And remember that this could be due to something random like mutation, or due to something that is not random like natural selection. Okay, the next thing is to discuss the 3 factors involved in natural selection as a mechanism. So we have to have that variation, we have to have heritability, and we have to have differential reproduction, which above we talked about as fitness, right? So we have to have all three of those factors in order for natural selection to occur, okay? Next is to explain the statement, natural selection acts on individuals, evolution occurs in populations. Okay, so this one we only kind of talked about. So in this case, right, we were taking away those white ones in our population, right? And so natural selection was acting on those individuals, right? Natural selection removed individuals or acted on them, okay? Not always removal, but there's also different things, okay? Versus like our ladybugs, we had natural selection acting on those spot patterns, where maybe rather than something being removed, it was better to have those 3 spots. Maybe it was sexual selection even, which we can talk about probably a little bit tomorrow, okay? So natural selection may be removed, individuals are selected for them in some way, but then evolution occurs in populations, right? So we had to look at the entire population to see the change in allele frequencies, right? Goes back to our definition of needing to have that change in allele frequency in the entire population, okay? Define the terms adaptation and fitness and relate them to evolution and natural selection. Okay, so we talked about fitness, but we actually haven't talked about evolution yet, or adaptation yet. So fitness is just the number of offspring, really, okay? So it's differential survival and reproduction is fitness, where maybe you don't survive to have any offspring, right? But then if you live to be 100 years old but never have a kid, your fitness is 0. Versus if you only live to be 30 but you've had 10 kids in that time, then you have really high fitness, okay? And then adaptation is where we have a certain trait that's beneficial in a certain environment, okay? Traits that are beneficial in certain environments. Okay, and when we're talking about adaptation in evolution, we're not talking about like, oh, I'm adapted to the, I'm like have adapted to the cold, you know, as far as like if I move back to Iowa where it's really cold in the wintertime, I will have to adapt to the cold, right? We use that term sometimes in our just daily lives, but when we're talking about adaptations, this is something that is in the genetics, okay? Where we have the genes to be better adapted for our specific environment. So those beans in the dark soil were, the brown beans were adapted to their environment. So natural selection maybe had acted on those genes to make it so that they are better adapted to that environment so that the predators can't see them as easily. Okay, so play with that definition and make sure that you understand kind of the vernacular, how we use it sometimes in daily life versus in the scientific definition, where we have specific traits being beneficial in certain environments and having that due to the genetics, okay? Due to genetics, right? So it has to be heritable, right? Okay. And then the last thing, determine which individuals, second to last, determine which individuals in a population have the highest fitness when given information about their reproductive success. So you should be able to, you know, give that example of being 100 versus 30, but the number of offspring is really what matters, right? So if I'm giving you the number of offspring, you should be able to do that, but you should also be able to do it in terms of XY graphs, right? Where we have a parent trait versus the number of offspring. Let's do instead, I don't know, we just did spots up there, didn't we? And we did color. Let's do something else. Let's do tail feathers. Okay, so maybe individuals that have fewer tail feathers, maybe, or intermediate numbers, are actually better. I'm thinking about like, what's that Dr. Seuss book, Gertrude McFuzz, where she has too many? So maybe there's 2, there's 4, there's 6, there's 8, and there's 10. Okay, and if you have too few, maybe sexual selection works against you. If you have too many, then maybe you're too heavy where you can't fly. So maybe it's best to actually have an intermediate number of tail feathers to have the most offspring. Okay, so here This would be a case of stabilizing selection, right? Where it's best to have the intermediate. Not too few, not too many. Intermediate is the best, okay? So for number 5, be able to look at this both in XY graphs as well as just being given the number of offspring, okay? All right, now let's look at our mutations one and our natural selection one. Make sure that we've just kind of got all of our different things checked off. And you guys are free to go to Dr. O's videos to look at this stuff a little bit more, or to my Echo 360s and look at these as well, okay? If you're feeling a little lost or there's just something that you want some clarification on. Also, feel free to email me. I was not feeling well last week, so I'm sorry I wasn't able to meet with anybody, but you can meet with me just by like asking me for a Zoom office hour anytime, and I'll see what I can do in my schedule as well, okay? Okay. So mutation. So describe the impact of mutations on the evolution of populations. So mutation alone can cause evolution, right? So mutations alone can cause evolution. And the other thing that I want you all to remember about evolution, or about mutations, is that they are random. And one more thing is that without mutations, evolution can't occur. And you're like, wait a minute, we haven't talked about that yet. We have actually, okay? So this, mutations create heritable variation. Right? So we need heritable variation in order for evolution to occur, whether that's random or through natural selection. Okay? And then categorize mutations, based on their effect on fitness. So we've kind of done this one before. I'm just going to start and put it down here. Right? So for number 2, we could have good or bad, or neutral, depending on environment. So we talked about this a little bit with those beans, right? Where it could be good to be the dark brown, it could be good to be light brown, it could be good to be white. It all depends on the environment. We also could have a population that has no predators, right? This happens on islands sometimes where there's no natural predators, and it makes it so that predator stress is removed, right? So that variable is removed. So maybe it doesn't matter what color you are in a certain environment, okay? Okay, so we've got mutations. And then the last thing that we talked about today was we started talking about selection. So let's talk about selection. Let's look at that quick too. Oh, somehow I got it done here. Okay, so selection here. Be able to discuss the various factors involved in natural selection as a mechanism of evolution and the effect of natural selection on populations. And then be given a scenario and look at the different types of natural selection occurring. Okay, so for these various factors, remember, these various factors are variation, heritability, right, and differential fitness. And those fitness differences are due to this heritable variation, okay? And so you have to have all 3 of these in order to have, natural selection occurring. Okay, and then given a scenario, state the different types. So remember, disruptive is where it's best to be extremes. Yep. Stabilizing is best to be intermediate. And directional is best to be one of the extremes. Okay, so I should be able to give you a scenario and then have you kind of play with what is the best option. Okay. All right, so I think that is it for today. I might talk a little bit about sexual selection tomorrow, but then I'll also talk about genetic drift and gene flow tomorrow as well. All right, play with this, and I'll have a bioconnection up for you guys as well. It's a kind of a different type of bioconnection, where it's a worksheet for you guys to work through. All right, have fun with that worksheet and let me know if and when you guys have questions that pop up. This is a real case example of something that is studied in the department, so I think you'll have fun with it. All right, bye y'all.